To go back to the beginning of the lecture on scatter, in this chapter, we learned that scatter is going to be created. It's one of the four primary interactions inside of the patient, and exit scatter is going to affect our image. So we have to deal with scatter in one of two ways, either before it's created or after it exits the patient's body. So either before it interacts with the patient or afterwards. So in summary, the amount of scatter that's going to be created is going to be determined by a number of different things. So KVP being the technical factor that will affect the creation of scatter. There are other technical factors as well that we've talked about. The amount of filtration is going to affect the percentage of scatter radiation. The change from single phase to three phase is going to affect scatter radiation. But realistically, the technical factor that you're going to use on a daily basis is going to be KVP. It's going to be rare that you're going to be using single phase equipment unless you're working in a doctor's clinic, and then it's going to be rare that you're going to have a single phase and a three phase machine side by side. It's going to be rare that you change out filtration, but those also can affect your scatter radiation. But in a practical sense, KVP is what you're going to be using. So KVP, increasing KVP increases total interactions inside of the patient's body. It increases the interactions especially when mass remains unchanged. So thinking about the Brim spectrum, as KVP goes up, we get an increase in production, we get an increase in peak energy, we get an increase in average. And what that equates to is percentage-wise, we get an increase in scatter production inside of the patient's body. So whenever we decrease mass using the 15% rule, then we get a decrease in the interactions, but we still have that increase in average and an increase in peak energy. So the percentage of scatter that remains in the beam in both cases is increased. So we have an increase in scatter radiation in the remnant beam. The amount of the remnant beam remains the same whenever the mass is decreased, yet we get an increase in scatter. What's left in the remnant beam is more scatter than straight penetration. So the percentage of scatter increases relative to the photoelectrics. Remembering our interactions, the photoelectric interactions actually go up because of the relative low energy of the average energy of the X-ray beam. But what's left in the X-ray beam is primarily scatter radiation. So the scatter relative to the PEs goes up. So what we have in decrease is fewer interactions inside of the patient's body and more scatter radiation. Whenever we decrease KVP, we have all of that reverses. We have fewer of the interactions become scatter radiation. More of the scatter that is created is absorbed inside of the patient's body, eventually becoming photoelectrics. So fewer exit the body. So as KVP goes up, scatter radiation to the image receptor increases. As KVP goes down, scatter radiation to the image receptor decreases. So tissue irradiated, as thickness goes up, scatter increases with increased thickness because primarily it's going to be soft tissue. The type of tissue that creates more scatter radiation is soft tissue. So as thickness goes up, we get an increase in scatter radiation. Volume, the volume, regardless of whether it's depth or width, increases the scatter radiation because you've irradiated more tissue. Going back to our possible interactions, again, we've got penetration, which volume of tissue really doesn't affect. You've got photoelectrics. That doesn't really affect the image negatively anyway. It affects patient dose negatively, but doesn't really affect the image, which is what we're interested in seeing here, in any way, negatively in any way. But the scatter radiation that is created in the tissue that you don't need to irradiate, it's going to cast scatter radiation over what you do need to see on the image. So whenever we increase our collimation, we reduce that scatter radiation. Again, increased collimation means more beam restriction, means a smaller field. Opening our collimation means reduced collimation. We get more scatter radiation. So collimate is the moral of the story. And then body composition, the top tissue that we're shooting through, it really depends. If we're shooting through more bone, we're going to get more absorption, and we're going to get scatter as well, but we're going to get more absorption in that bone. And if we're shooting through soft tissue, then we're going to get an increase in scatter radiation. So how does scatter add to the image? It adds density, it's overall density. It reduces contrast. So in reducing contrast, we have a longer grayscale and higher latitude. It gets less black and white and it gets more gray. So density, that's if KVP goes up. If KVP goes down, everything reverses. As KVP goes down, we get a shorter grayscale. It's more black and white, and latitude goes down. So increased KVP, long grayscale, high latitude, long scale contrast. Low KVP, short scale contrast, high contrast, and low latitude. Does not affect changes in KVP or scatter radiation creation, rather, in any way. Does not affect sharpness or recorded detail. It only affects visibility or recorded detail. So technical compensation for increased beam limitation, again, it's mass. If we increase our collimation, then what we get is a reduction in numbers. So unfortunately, we lose some density. The density is fog, so it's really kind of a good thing, but we need to increase our mass. Beam limitation limits the scatter radiation, so and the scatter being a density, if we increase collimation, we have to increase our mass. If we increase KVP, we would increase scatter radiation. That's what we're trying to get rid of. So we don't want to increase KVP to compensate for beam limitation. We want to increase mass, because increasing KVP would be counterproductive to controlling the scatter, which is what we're trying to accomplish from an imaging standpoint by increasing our collimation. Remember, collimation originally was radiation safety, radiation protection, lowering radiation dose, and imaging, the purpose for collimation, increasing collimation, is scatter removal. So if you increase KVP, then you reintroduce the scatter that you just eliminated. So how you compensate when you're using AECs is you don't do anything. If you increase your collimation, then again, your photocells can't really differentiate between scatter radiation and transmitted X-ray photons that are non-scattered. Your phototimer is just a radiation counter. So if it receives enough radiation, regardless of whether it's scatter or non-scattered photons, then it terminates the exposure whenever it gets to the desired quantity of exposure. So if you collimate, basically what it's going to do is it's going to give you a higher mass naturally. You don't manipulate the AECs. The AECs detect the proper amount of radiation and they terminate the exposure whenever they're ready to. So if you're phototiming, you don't have to adjust anything for your increase in collimation. So that brings us to the final thing that we're going to talk about this semester, and that is how to get rid of scatter radiation once it's created. Primarily, we're going to use grids, and this is a very simplistic view of grids. We don't have grids that look anything like the one that's demonstrated here, but it serves a good purpose in showing you how grids work. So, what is a grid? A grid is a device that we put behind the patient to absorb scatter radiation that's created within the patient and emitted. So it's in the secondary beam. We put a grid in the secondary beam to clean up that secondary beam, the remnant beam. And they're constructed of alternating strips of radiolucent material and radiopaque material. So radiolucent material is something that X-rays easily penetrate, as opposed to radiopaque material, in this case being lead. The lead absorbs X-rays. So that sounds like a bad thing. We're putting something in the remnant beam that absorbs X-rays. And in a way, it kind of is a bad thing. But we're going to deal with the bad part and end up with a better product in our final image. So it was developed by Gustav Bucky in order to clean up scatter radiation and make a higher quality image. So they're designed to transmit only X-rays traveling in a straight path from the tube to the image receptor, and that goes through the interspace material.